dealing with patterns and non-linear functions today. So you're going to have functions that are linear and non-linear. Remember, straight line linear functions are ones that give you straight lines. So that means a non-linear function is a function whose graph is not a straight line, which actually is most. In Algebra 1, in Algebra, we do a lot of straight line stuff, but you also start doing a lot of non-straight line, a lot of non-linear equations. A lot of things can be modeled by non-linear equations, so we use them more and more as time goes on. So these are examples of linear equations. They give us a straight line or a linear function. Which means that these ones down here would be non-linear. Linear, non-linear. Either they make a straight line or they don't make a straight line. Okay. We don't break down non-linear ones in particular very often, but there are a few. These are the three most common ones that you deal with, or a couple of them. These are quadratics. This is a parabola. I'm sure you've seen it before. You will see it again. This is a cubic. This is modeled by x cubed, x to the third power. This is what an absolute value equation would look like. We're going to work with those two before the year is over. So we're going to work with we're not going to work with the one in the middle too much, but we will work with the other two often, particularly as we get in the second semester. All right, so classifying a function as linear or nonlinear is actually pretty straightforward for this. The area in A in square inches of a pizza is a function of its radius, R, in inches. The cost C of dollars in pizza sauce is a function of weight in ounces of sauce used. Graph these functions shown by the tables below. Is each linear or nonlinear? So here's what I want you to do. Plot these points. The first one, you have the radius on the bottom, square inches on the top. You can't be exact, but do the best you can. Okay, you cannot get exactly 12.57, but you can go a little bit up. For 40, you can do 50. You can get approximately what it is when you graph it. So take a minute, graph these points, connect the dots. Do the same thing for the second one. Graph the points, connect the dots. Okay, so I'll scroll this up to make it a little easier to see. So 12.5 is right about here. 4, just a little more than 50. 6, 113, right about here. 8, 201. And then 10, 314.16. And if you connect the dots, you don't quite get a linear equation. It does have a bit of a curve. And what is the formula? What is the formula for area? Area pi r squared. Because I'm squaring the radius, that makes it not a linear function. That's the whole point. That's what makes it nonlinear. If it was a straight line one, it wouldn't be that. Looking at the table, each one of these all go up by 2 each time. But the ones on the other side do not go up by the same amount each time. If these went up by the same amount, it would be linear. These don't. These go up by 2. These don't go up by the same amount each time. It's nonlinear if they don't go up or down by the same amount each time. I plot this one out. Let's see, 2 and 80, 4 and 160, 6 and 240, 8 and 320, and 10 and $4 even. And those you do connect up in a straight line. So this one is nonlinear. And this one is linear. And we talked about linear functions the other day. Each one of these go up by 2 each time. And this one goes up by 0.8. Each time. It goes up by the same each time on both of them. It's the same difference each time. It's a linear equation. Okay. Questions about that? Plot the points, you get a curve, it's nonlinear. You plot the points, you get a straight line, it's linear. Okay, we did the same thing here. We did the same thing the other day, only with straight lines. Okay, representing a non-linear function. Table table below shows the number of blocks in each figure below is a function of the number of blocks on one edge. So edge length is x, the number of blocks on an edge is x. The number of blocks in the whole thing is y. So you've got the first two here, or first three. First block, 1 block on an edge, you got 1 block on the bottom. You got 2 on the edge, you have 8 altogether. You have 3 on an edge, you've got 9 altogether. So if I were to do the next one, it would have 4 on one side, and 4 on that side, and 4 on that side. How many would that be altogether? How do I get 2? How do I go from 2 to 8 and from 3 to 9? Does anybody know? Or 3 to 27. What's the relationship between these? Does anybody know? Because you should start knowing these numbers. If I have 4, then I have 64 blocks, so my point is 264. If I have a 5 by 5 by 5, and I know it's not to scale, I get 125. So that would be 5, 125. Does anybody here recognize those numbers? Because that is something you should be learning. You should start to know, particularly these first 5. They're perfect cubes. 1 cubed, 2 cubed, 3 cubed, 4 cubed, and 5 cubed. That's where we call it a cube. Something in the third power is called a cube because that's the volume of a cube with that on one side. That's where the term cubed for something to the third power comes from. Something squared comes from the area of a square with that side. That's why something to the second power is called a perfect square. That's where these terms come from. These are perfect cubes, 1 through 5 cubed. You should really know 1 through 5 cubed. Those numbers you should try to commit to memory at some point. They will help you a lot in your future, in this class and others to follow. So, just like last time, we had to complete the table, got to come up with a description in words, got to come up with a graph, and have to come up with an equation. Okay, so, in words, the number of blocks, the total number of blocks is the cube of the side length. Oh, I spelled it backwards. GTH. The number of blocks in a cube is equal to the cube of one of the side lengths. That's why we call something to the third power a cube. length times width times depth. If they're all the same, it's a perfect cube. Our equation, the number of blocks, y, from the table, equals the side length cubed, y cubed. And then for the graph, plot the points. 1, 1, 2, that's not 1, 1, that's 125, 1, 1. 2, 8, 3, 27, 4, 64, 5, 125. And 6 is way, way up there because it's 216. And what is 0 cubed? If I have a cube with no blocks making up the side length, how many blocks are in the whole volume? If I have this shape where there are no blocks length at all, how many blocks do I have in the whole thing? 0. If I have a side length of 0 and a height of 0 and a width of 0, that means there aren't any blocks there. So the point 0, 0 is accurate. And if you connect them up, you can definitely see where that is nonlinear. It does not grow the same amount each time. It's got a pretty nice little curve to it. Questions about that? You should learn your perfect cubes as time goes on. Now you try. The table below shows the number of new branches in each figure in the pattern below. What is the pattern you can use to complete the table? Represent this relationship using words, an equation, and a graph. Early computer-generated animation. When they first started making animation with a computer, the computer was actually generating the whole thing. They weren't drawing by hand when they were writing the equations to do it. This is some of the first stuff they did, making trees and things. And this is exactly how they did it. They just decided how bushy they wanted to make it, and they told it to go so many steps out. But that's exactly what they did. They wrote a program that did this. Okay. So the number of branches go out, it's the same thing, same set of numbers. Okay, so it's 1, 3. When I get to the next, there's 3 branches that come off, and then there's 9 branches that come off, and then there's 27 that branches come off. How am I getting from 3 to 9? From 9 to 27, what am I doing? Multiplying by 3. So the next one would be 27 times 3, which is 81, and then the next one after that would be 81 times 3, which is 243. 243. Okay, so in words. So this is not actually, this is a little bit harder one to describe. In words, the number of new branches is 3 times the previous number. Previous. Previous. No. Previous. No, that's okay. It's not. I'm really not very good at spelling a lot of things, but certain words like this one I'm actually pretty good at. There's a few of them. The odd ones I tend to be better at than the easy ones. Yeah, and yeah, the previous number of branches. Now, plotting out the graph, that's not that hard. You got 1, 3, 2, 9, 3, 27, 4, 81, 5, 243. It's a really steep curve. The equation for this is actually much harder than the other ones. It's an exponential. It's 3 to the x. Because I'm doing this, I'm taking 3. This is 3 to the first power. Guys, so if I look at this one here, this is actually 3 to the first, 3 squared, 3 cubed, 3 to the fourth, and 3 to the fifth power. I do not expect you guys to recognize that. That's okay. I would never expect you to get that equation when this was a test. Okay, I know my other 2 kids have a tough time with that one until after we really, really worked on it later on this year. I don't get to them until second semester. Okay, and that's it.